Class of Materials Engineering was distributed into 3 to 4 groups. Each team was given a part from a chainsaw on which they would have to perform various tasks to determine the part's material and come up with ideas on how to improve it. We were allocated the crankshaft of the chainsaw. The practical sessions were conducted in weeks 7 and 8. Different tests were performed by every group depending on the part they got. We performed a total of 5 tests on our crankshaft. 3 tests were performed in week 7 and 2 were performed in week 8. So the tests that we performed were the 3-point bend tests, tensile tests, density tests, hardness test, and microstructure test. Samples specific to each test are shown here. 3-point bend test.
J crane, specimen 6, and response plan is 7. Thickness would be.
So for sample 6, the thickness is 2.09.
And the width
18.14.
then you press.
So
You press the load and then you press balance load. Pushing it, so it's from here. Let's go. So this time.
yeah, go back up. Get this around 200.
Alright, that's good.
Yep. And then 0 extension.
Zero extension, start.
Sweet. I have really shaky hands. This isn't gonna look good. Extremely similar.
I reckon it's the same thing.
Hmm. Tensile testing.
We are class 30 and group 2. We are doing tensile testing for our material verification. So we have already done 2 samples. Here are the results. We are doing our third and last sample, sample 3. So in order to start the test, first it has to be loaded in the grid. And sorry, you have to put 2 dots as we will use the Blue Hill 3 software to measure the length between them.
Yeah.
So you load them here.
Yep.
You then you come to the software. You come here and see this camera, you click it. So then you come here and select measure. This will measure the length between the dots that we put earlier before loading the specimen. It does that by using the camera built in the machine. Length, which is 20.119 millimeters. Press OK here. You come here to input some of the data required by the software. 20.119. You come here with putting in all the measurements and the dimensions. You come here and see rate. The rate has to be constant for all the samples that you're doing. We are using 5 millimeters per minute. You come here and then balance load, 0 extension. You come here then and then press start. As you can clearly see, we have already done 2 samples. These are the graphs for that. And now we are doing our last sample. Has done, and by the look of the graph, it was successful, all of them, hopefully. And as we
Hardness testing.
measure, right?
Got it. Sorry. Microstructure testing.
Test for microstructure. This is our sample right here. We're grouping. You come here, you place the sample right on the microscope. So you have to make sure that the silver lining is exactly here. So that would help with the microscope lens in order to, as you can see, we have our image now.
Yep.
We can choose the lenses from the objective magnification lens, and we have some options here on the microscope that would help us definitely to get a better sample so we can judge our material.
Yep.
As we have light and we have autofocus. So you just come here and then you adjust the autofocus to get a better result. It takes 3 seconds to get a new image in the computer.
Yep.
So as you can see, as slowly I move the focus, the picture keeps getting better until it starts disrupting. I have to stop it. As you can see, the photo has now been slightly being blurry, so I go back. This is the best we can get from this lens. So you just come here and snap, and as you can see, all the data has been transferred to a USB, which we will use in our group report.
Yep.
We now, after saving, we just come here and manually just change the lens to number 10.
Make sure it clicks into place.
And we have to make sure that it clicks just like that.
Yep.
And then you just come here to object magnification, click number 10, and then again you just play around with the brightness and with the autofocus just a little bit. This is the best picture we can get out of the 10 magnification lens. You just come here and then snap.
Yep.
We have 4 different lenses, so we do the same step for each lens.
Density. Finally, we couldn't record any footage for the density testing, so pause the video for a step-by-step of what we did. Values from the tests. After the testing was complete, we recorded our values and graphed the 3-point bend and tensile test results.
We have now moved to part 2 of our experiment, which I said before is to process the data that we got from our test in the weekly sessions, which mainly being our 3-point bend test and tensile testing. A total of 6 tests were performed, and we got our data in Excel data points. We now have to calculate stress and strain from this and make graphs which will then help in taking an important values, which will then help in determining the material from the CES software. This is how we got our data in an Excel sheet with dimensions in upper right corner, extension in millimeters, and load in kilonewton. We now have to calculate strain first. The formula for strain is change in length divided by original length. So we come here, type strain. Our change in length here is extension divided by the original length. The original length as said before, is mentioned up here, which being here is 70. Enter. Now you drag the cell all the way down, which then copies the formula for each of the individual points. This is our strain for this experiment. We have to calculate the stress. The formula for stress is 4 divided by the cross-sectional area. However, the force should be in newtons, but here the force is given us in kilonewtons. So first we will change the load from kilonewtons to newtons. So load in newtons is equals to. So we do know that there are 1000 newtons in 1 kilonewtons. So the value of kilonewtons multiplied by 1000 into. So this is our Newton now. So we do exactly the same. We drag it all the way down. So this is our value of load in newtons for the whole experiment that was conducted. Now we can easily calculate the stress. The unit for our stress here is in megapascals, which is newtons per millimeter. You press is equals to newtons divided by bracket open, as we have to take area, cross-sectional area. So here are the dimensions, 2.11 into 18.14. 18. Enter. So this is our stress. We just copy the stress all the way down. Just drag the whole cell down. Stress. We will now make a graph of this. As we can see, this is our graph for the experiment that we conducted, with stress is on the y-axis and strain is on the x-axis. So this is our graph after calculating all of the values. So these are the values which we calculate from a stress versus strain graph of a 3-point bend test, which being the ultimate bending stress, 0.2% offset Eastern, the points, and these are the points that we use for our Young modulus. In other words, the gradient. And this is our point of elongation, the final elongation or the fracture point. The same tests were carried out for the rest of the 2 tests of the experiment of 3-point bend testing. We are now looking at how the graphs were plotted in an Excel sheet in order to find some important tensile testing values, such as ultimate tensile strength, to 0.2% offset yield strength, elongation, and Young modulus. So first of all, we have to calculate. So first of all, this is the way how the data was given to us in Excel sheets. These are all the data points, and on the upper right corner we have dimensions with followed by the test rate. So the extension is given to us in millimeters and the load is given to us in newtons. First of all, we have to find the strain. The formula to find our strain is a change in length, or the extension, divided by the original length. So in order to put a formula for which could be then copied to all of the cells in order to get the strain for the whole data sheet, we have to press is equals to, select the cell for extension, divided by the original length, which is just given us here, which is 25.79. 25. You just press enter. So if we increase this, we can see this is the length, width, and thickness. So this is the strain for these 2 particular points. So in order to find the strain for all of the shade, we just click on this and drag it all the way down. This is the strain for our whole data sheet. We now have to calculate stress. We may follow the similar steps. The formula for stress is 4 divided by the cross-sectional area. The area in this case will be taken through width into thickness. So as the units that we are taking is newtons for the load or the force and millimeters for the area, so our unit would be in megapascals. So you press is equals to, select your load, divided by, bracket open, as this is a multiplication in order to find an area, 7.16, which is the width, into 2.17, which is the thickness. Press enter. So this is our stress. Similarly, we just drag the whole way down. So this is the stress for the whole data sheet. So now in order to plot a graph from the stress and strain values that we have, we select both of the values, come to insert, and then plot graph. So this is the graph. So as you can see, the graph is as it should be with our elastic region right here with turning and slow deformation. And this is the point where the object had fractured. So after editing and finding out all the necessary values, this is how our graphs look like. This is the heading for sample 1. This is the ultimate tensile strength, elongation point or the point of fracture. These are the points which we're using in order to find the Young modulus of the point.
Hardness and microstructure. We didn't do any calculations for the microstructure and hardness testing, as all the values were provided to us by the testing machines. Finding the materials from CES. Once our data is collected, we transfer our results to the software CES.
We are now looking at how to find a material or how we found our material on the CES. As you can see that we already have level 3 selected as that was a prerequisite demand of the question. After this, we have to come to the limit option so that we can find the values. So we can put in the values that we found from the test that we conducted in our practical sessions. So you come here and chart and select limit. This way, this is a limit in which you can order any limit. For us, that would be the physical properties and the mechanical properties. So we have density in all of these limits, so we have to enter a minimum and a maximum value. We can also enter either each one of them, and then that helps us filter the material and will help us find the materials. So we will now start entering our material property that we found through our test. So these are the values that we have entered: density, yield strength, tensile strength, elongation, and hardness because value. These are the values that were found from multiple tests. For example, hardness value was found from the hardness test, tensile strength was found from tensile test, and then density was found by density strength. After we have entered these values, we just come in and press apply. So you can see from almost 3,968 materials, this material was found, which is carbon steel, water quenched. So these are the properties of the material that was found, and if we come down, we can see that these are the material properties and we can match them to our results. If we have a quick look We can also see the typical uses of a material. That can also help us determine a material if we found a wrong or correct material. Our part of the chainsaw was the crankshaft of the chainsaw, and it here says typical uses: heavy duty shafts, axis, crankshafts. So that means the material that we found is reasonably correct because it says the typical uses is for a crankshaft.
Redesign of the crankshaft. During the redesign process, we thought of how we could improve the crankshaft from a more mechanical mindset, as the aesthetic component becomes irrelevant once submerged in the chainsaw. We looked towards two main components in general, the bearings and the counterweights. On a side note, we believe the crankshaft is at a stage where there's not much more you can do to it in terms of upgrade. It's common to have the bearings in a crankshaft wear out over time due to fatigue or excessive revving. So that is why we are focusing on this aspect. More so, bad bearings result in up and down play of the crankshaft, vibration and squealing. Failure after continued use will most likely lead to damaging other parts of the saw. Because chainsaws are being built cheaper and cheaper these days, counterbalancers might not be built to a high standard. In a car, the counterweights have to be perfect. Precision cuts by machinery could be an option in a redesign. Most chainsaw crankshafts are equipped with steel ball bearings as they are cheap. Ceramic bearings would definitely be an upgrade as they would reduce the weight, are a much harder material so it wouldn't break down as quickly, and is resistant to corrosion. Each counterweight is designed specifically for the rod and piston combination, so from a mechanical point of view, redesigning the weights would be pointless. Although this is the case, we still designed a more defined shape to get a better understanding of an alternative option for a counterweight. So in conclusion, we have changed the bearings from steel ball to ceramic and show a more precision cut counterweight for a longer lasting life cycle.